All right. Hi again, everybody. Here's your asynchronous work for your first weekend of Calc 1. I'm going to talk a little bit about continuity from 1.3. And then after that, I'm just going to dip a little bit into talking about limits using the squeeze theorem in 1.4. I think my pencil is not going to show up well. Let me switch over to a pen here. Never use pen. I have one that works. 1.3. This is continuity. So the definition here is for continuity at a number. The definition is really important. Our definitions are usually very important, but we're going to be going back to talking about continuity in so many different sections where we're going to be having continuity as a condition that needs to be met. So it's really important that we're able to understand the concept of continuity so that we can later on show that our functions are continuous. A function is continuous at a number c if the following three conditions are met. Okay, so I'm going to give you three conditions here, and then I'm going to give you some examples where we're going to check these conditions. The first is that f of c is defined. That means that c must be in the domain of f. The next condition is that the limit as x approaches c of f of x exists. And then the third is that the limit as x approaches c of f of x equals f of c. Okay. So a function is continuous at a number c if the following three conditions are met. The function has to be defined at that value. The limit must exist, and the limit of the function as x approaches that value c has to be equal to the actual function value at c. A continuous function's graph can be drawn without ever lifting your pencil. You might want to make a note of that. A continuous function's graph can be drawn without ever lifting your pencil. I do feel that in general, continuity is a topic that students tend to do really well with. It seems to be pretty intuitive. So example one, we're going to discuss the continuity. Continuity. The first one I want to look at, and I'm going to show you a couple different types of functions here so you can sort of compare and contrast. is f of x equals x squared minus 4 divided by x plus 2. Now, I think that we looked at this function earlier today. Well, I don't know when you're watching this, but we were talking about how to find the limit of this function, and we redefined it. It might have been a x minus 2 in the denominator, but it was very similar. All right, so we're looking at this function. We don't know a whole lot about it, but what you should be noticing right off the bat is that you can simplify this function out. And if you're wondering, well, why would I need to simplify it? Well, that's something you might want to consider, just because the function that you're looking at right now has an issue with the domain. If you let x be -2, the function doesn't exist at -2. So we're going to address that in terms of continuity. So if you have a situation like this with your function, you're being asked to discuss the continuity, if you can simplify it and cancel something out, you should try to do so. So let's go ahead and rewrite the numerator as x plus 2 times x minus 2. And when you do that, you can see that you end up with these common factors of x plus 2 in the numerator and the denominator. When you cancel those out, you end up getting this equivalent function, x minus 2. Now, the graph of the equivalent function, x minus 2, is going to look almost exactly the same as the graph of the original function. The big difference is that you cannot actually define your original function at -2, but you can define your equivalent function at -2. But the graphs are going to look almost exactly the same. If you were to graph this function, and we'll also do this in our calculators, but it's got the y-intercept at -2, and it's got a slope of +1. So it's going to go up 1 over 1. And it's going to do something like this. And you cannot actually define this, however, at -2. So if you were to take this the other direction, you would end up getting a hole in the graph right there. And this might also seem weird to you because you're thinking like, wait a second, x squared minus 4, isn't that quadratic? Yeah, but you take a quadratic and you divide it by linear. And you guys spent some time doing long division of polynomials in your algebra class. You can kind of see where this comes from. If you want to see this on your graphing calculator, I need to go brighter or less bright. We'll see. We can graph this as x squared minus 4 divided by x plus 2. I'll go to standard zoom. Now, what's interesting about this is you can't actually see the hole in your graph. You know, sometimes if I zoom in really, really closely, I can see where they've tried to leave a pixel out so that you can see a hole in the graph. You might be able to do that if we zoom in really closely. I don't know if it's worth trying, but you can definitely see it in the table. If you were to actually try to evaluate this function at -2, you'd get an error. By the way, if you want to see the equivalent function, your equivalent function is x minus 2. If you were to graph that, watch how this is going to graph right over the function that we already have. Okay, it's kind of hard to see the color change here, but it's just the exact same line. However, when you go to your table now, notice you have a second column for y sub 2. This is for the equivalent function, and you do indeed get a y value at x equals -2. The y value would be -4. All of this leads you to the conclusion that this is a removable discontinuity. We had an original function, but we were able to rewrite it in such a way that the equivalent function no longer had that issue with the domain. So we would consider this to be a removable discontinuity. You might want to go ahead and make a note about the domain. So we said that x plus 2 can't be equal to 0 and x cannot be equal to -2. that tells us that we're looking at the value c equals -2 as far as continuity is concerned, because anywhere else on this graph, we don't need to worry about whether or not the function is continuous, because the only value that's excluded from the domain is this one. So that's kind of why we've been focusing on this place where you end up seeing this hole in the graph. So we're going to say that there's a hole or a removable discontinuity at x equals -2. Now, if you're not sure, like, how would I know that I have a removable discontinuity? Well, I am going to show you some examples where you have non-removable discontinuities, and that's going to happen most often. But one of the ways you know your discontinuity is removable, well, two ways. Like, the big indicator is that you can cancel something out and then get rid of that issue with the domain. But you're also going to end up seeing this hole in your graph. So every other value on your function is defined except for one of them. And then as you continue on, every other value is defined. One student once told me that he considered a removable discontinuity to be a situation where you're driving along the road and then you hit a pothole and you go over it and you keep going. And I liked that description of the removable discontinuity. Because it is very different from the infinite discontinuity, which we're going to talk about in a minute. So this happens when we can redefine the function at c, basically. So this occurs when we can redefine the function at c. If you're thinking about the definition that we originally stated for continuity, we said a function's continuous if the following three conditions are met. Well, the first one was that f of c is defined, and we didn't have that because we did not have the function being defined at -2, clearly. So that's one way that we know that the function was not continuous at -2. Now, once you violate one condition, it doesn't even matter if the other ones are met, because all you need to do is violate one to have a discontinuity occur. But notice that the limit does exist as the values of x on each side of -2 are approaching -2. You still end up getting the limit to be -4. So the limit does exist. The limit can't possibly equal the function value, however, because the function value at -2 doesn't exist. So you actually violate conditions 1 and 3. And this is because f of -2 does not exist. However, as far as places where your function is continuous, we would say that f of x is continuous on its entire domain, and the domain does not include -2. So a lot of times I'm going to abbreviate continuous because it gets to be cumbersome to keep writing it over and over again. So I'll say f of x is continuous on the interval from -∞ to -2. And then I'll pick that interval up again at -2 and send it off to infinity, just to write that in interval notation. Okay. All right, so that's an example of a removable discontinuity. So I want you to be thinking as I go through these examples about what types of questions you're going to be asked here. And on your exam, I would say something like discuss the continuity. And I would give you a function like this. And you're looking for places where the function might not be continuous. You're going to pick out places where maybe the function does not exist. So we decided, okay, the domain does not include -2. That's a problem area. If you can redefine the function, which I did here, then at least you know that it's removable. There are going to be a lot of cases where you can't redefine the function, and then we'll talk about what kind of discontinuity that would bring. So as far as discussing the continuity, we're just stating that it's continuous on this interval, but there is a whole or a removable discontinuity for x equals -2. So let's contrast that with your reciprocal function. This will be example 1b. F of x equals 1 over x. This was another one from your library of functions in college algebra. You should have spent a lot of time working on this function. Right off the bat, you're going to notice that if x equals 0, you have a big problem because your function is not going to be defined at 0. So we could say that because f of 0 does not exist, the function is not continuous. At x equals 0. Remember here talking about these conditions for being continuous. The first one was that your function has to be defined at the value c. Well, we just found a value c, which was 0, for which the function was not defined. So that's problematic for us. So if the function doesn't exist at a value, it can't possibly be continuous there. Now, if you remember what the graph of your reciprocal function looks like, this is one we'll use quite a bit. You'll see it a lot also in Calc 2, so we should become very familiar with it. If x is 1, f of x is 1 over 1. So if x is 2, f of x is a half. If x is 2, if x is 2, f of x is a half. If x is a half, f of x is 2. So this is called a reciprocal function because the y value is always going to be the reciprocal of the x value. So it kind of looks like this. And it's got these two wings to it. It is symmetric about the origin. If you remember your symmetry, it's an odd function. You'll always know a function is symmetric about the origin because you can flip it upside down and the picture looks exactly the same. So that's your reciprocal function, f of x equals 1 over x. Now, there's a big difference between example A and example B. For example B, I cannot rewrite this function in order to cancel out this x in the denominator. So thinking back to the last example, we were able to factor and cancel, and then my new function, which had a graph that looked pretty much equivalent, didn't have an issue with the domain. I cannot possibly rewrite 1 over x. There's no way that I can cancel out that discontinuity in the denominator. Because of that, I would say that it is a non-removable discontinuity at x equals 0. I would say f has a non-removable discontinuity at x equals 0. We cannot redefine the function so that we end up having f of 0 existing. We also would say that in this situation, the discontinuity is infinite. Usually an infinite discontinuity is going to occur when you have this asymptotic behavior. Clearly you have this vertical asymptote at x equals 0. It's an infinite discontinuity differs from a hole because a hole is the pothole that you just drive your car over and you keep going. This is not a pothole situation. This is just like one leg is veering off into one part of the universe and the other leg is hopping off to another. you can't just drive your car over this and keep going. You'd have to just completely jump from one graph to the next. You might also want to note, underline these keywords, non-removable and infinite. There's a vertical asymptote at x equals 0. You guys spent some time talking about how to find vertical asymptotes in your algebra class. If you don't remember, I'm going to remind you next week. We'll talk about vertical and horizontal asymptotes. So you're going to get more practice with those. But what we do want to do is discuss the continuity. So we already talked about places where your function was not continuous. So we will say that f is continuous on its domain. And its domain is all real numbers except 0. Anywhere else, there's no issue with the continuity. I can graph this anywhere I want. I never have to pick up my pencil, except, yikes, if I try to get from one leg to the other, that's a big problem. And then once I do that, I just can keep graphing this without ever having to lift my pencil. And this one violates these conditions of continuity also. Condition 1 is that f of c has to be defined. It's not. So violates conditions. Let's see. 1, because f of c does not exist. Condition 2 is that the limit exists. Well, the limit clearly does not exist as 0. You're not approaching a particular value here as you head towards 0 from the left and from the right. And then clearly, if the limit does not exist, then it can't possibly equal the function value, which also does not exist. So there are some major problems with this when you violate every single condition of your definition. Okay, so to recap, this one is continuous on its domain, which does not include 0. We would say that the discontinuity is non-removable because we can't redefine the function to get rid of it, and the discontinuity is infinite. Let us do a piecewise function. Your daily piecewise function has arrived. F of x equals, this will be in 2 pieces, x squared and negative 3x minus 2. So the x squared will be for x less than negative 1. And then the negative 3x minus 2 will be for x greater than or equal to negative 1. Okay. A lot of times for these piecewise functions, you just will have to graph them. I mean, there's a little bit of analytical work that you could do as far as finding the limit and looking at the limit in terms of the function values. With continuity, a lot of times it's most helpful to graph the function and actually look at it. Because I think as far as continuity is concerned, our mind finds it easy to look for pieces in the graph where it's not connected versus like trying to examine the data. So let's go ahead and graph this piecewise function. F of x equals x squared for x being less than negative 1. Well, remember, I want to put an open circle at this boundary point. So if x is equal to negative 1, well, negative 1 squared is positive 1. So I would have an open circle here. And then if x is negative 2, y is 4. And if x is negative 3, y is 9. So somewhere up here, I'm at like a weird angle. Okay, so we'll have this situation. It is a parabola. I'm trying to make mine look like a parabola, but that's as good as it's going to get. And I left this open circle, remember, at negative 1, 1, because my graph is not actually defined on this piece for x equals negative 1. So we left that open. But we don't want to just not include it, because, I mean, what if we just started at x equals -2? Our graph would have started here, and you'd be missing this whole segment between -1 and -2. That's a lot to be missing off your graph. Okay. So let's graph the other piece of this. Now, this is going to occur for x being greater than or equal to -1. It's got a y-intercept at -2. And the slope is -3. So that means that as you move from left to right, your line is actually going down. So 1, 2, 3, 1, something like that. We could do that one more time. It's not really going to benefit us to head off this way, because I really want to know what's happening as I move up towards -1. I can use the slope and go up 1, 2, 3, and left 1. And if you don't believe me, you can always plug that point in. If you let x be equal to -1, you'll get +3 minus 2, which is +1. And that circle is going to get filled in now. So notice that we did not fill it in previously because we had obtained it from this first line of our definition. But now we are filling it in because in the second line of the definition, our function is actually defined at -1 as 1. So this is the graph of our piecewise function. This is normally the part in class where I would ask you if you have questions. Now it's just me and the hydration station. Okay. All right. Now, people tend to think that when you have a piecewise function, of course, you're going to have a major discontinuity, because we're used to seeing these in pieces where you have this major disconnection. But that's not occurring here. Think about the definition here for continuity. First of all, the place where we would be looking for our problems would be at -1. Okay, so note any discontinuity would occur at c equals -1, which is your boundary. This is where your graphs would switch. If we did have a discontinuity, that's where it would occur. X squared is a polynomial, so it's going to be continuous on its domain. And then -3x minus 2 is also a polynomial, continuous on its domain. So if we had a discontinuity, we'd be expecting to find it here. So the conditions for our continuity, well, the first one would be that f of c exists. F of -1 exists. Yes, it does. When x equals -1, we have a value of +1. Check. The second condition for continuity was that the limit as x approaches c exists. So we can look at that. Now, talking about the limit, I mean, clearly you can see that the limit would exist, but if you want to think about it in terms of left and right-hand limits, even though your function did not actually define -1 for this first piece, you can still see that the limit as you approach -1 from the left would be +1. And then this function ended up already being defined there anyway based on the function that we are arriving at from the right. So the limit exists, yes, because the limit on the left is 1. The limit as we approach -1 from the right is also 1. So you could say that the limit of f of x as x approaches -1 is 1. It exists. The third condition is that the limit must be equal to the function value. And that's true too, because f of -1 would follow this definition, and f of -1 would be equal to +1. And we just said that the limit is also +1. Check. So we actually don't have a discontinuity at c equals -1. So we could say that this function is continuous on its entire domain, which is all real numbers. You can draw this entire graph without ever having to lift your pencil. There's no hole in it. There's nothing to skip over. You just keep drawing. Now that I've said that, I feel like someone's going to be wondering, like, well, what if there was a hole here? And yeah, technically, like, what if I had defined this as x being less than -1, and then I had defined the second line as x being greater than -1? And what if I did not give you greater than or equal to? Well, if that was the case, then you would have a hole here at 1, and that would be a minor issue. If you had a hole there at -1, you'd have something you have to jump over, and then yeah, you'd have a discontinuity in your graph because you wouldn't be able to graph the whole thing. But I did not define it that way. You can graph the whole thing without ever having to lift your pencil. Okay, so that's what I wanted to say about that. Let's do one more piecewise function and talk about continuity a little bit more with piecewise functions. So the last one for this is D. The function we're going to define in two pieces. The first one is x, and that's for x being less than 1. And the second one is 2, and this is for x being greater than or equal to 1. Okay, and again, it's a piecewise function. A lot of times it's easiest to discuss the continuity of a piecewise function when you're looking at its graph. If x is less than 1, y is x. Now, again, we're going to look at what actually happens at 1, and we'll leave an open circle there. So if x is equal to 1, if I were to graph y equals x, I would have, if x is 1, y is 1, leave an open circle there. And then we're looking at values of x that are less than 1. So if x is 0, well, f of x is also 0. And you get this identity function where you have that 45-degree diagonal. And who cares what it does at this point? It's going to just keep doing its thing as it heads off into the sunset towards -infinity. If x is greater than or equal to 1, f of x is 2. So if x equals 1, f of x is 2. If x equals 2, f of x is 2, so on and so forth. F of x is 2 is just this horizontal line. And there's your graph. I guess I don't really need to do this. If you wanted to see something, you could just pause the video. Such is life. Okay. So clearly you have this continuity here. And of course, it's happening at the boundary. So we're going to say it's a possible discontinuity. Continuity. So if you were going to have one, it was going to happen there. And sure enough, you do have a discontinuity here. You cannot graph this without ever having to lift your pencil. I also would not say that this is a removable discontinuity because it's not a situation where like I just have to run my car over it and then keep going because I would have to switch roads at that point. But I also wouldn't say it's an infinite discontinuity because it doesn't just head off towards some, infinite, some value approaching infinity. It doesn't do that. It's not like it's an asymptote. So we have a different name for this, and it's called a jump discontinuity. So there's a jump discontinuity at x equals 1. A jump discontinuity occurs when the one-sided limits exist but are not equal. So if you're thinking about these one-sided limits as you would, the limit as you approach 1 from the left is +1. The limit as x approaches 1 from the right is 2. So this is a problem because 1 is not equal to. And that's where you end up getting this jump discontinuity. Now, again, notice the difference. It must be the case that the one-sided limits exist but are not equal. And with this infinite discontinuity, we didn't have that case. The one-sided limits here actually did not exist because we wouldn't say that infinity exists as a limit anyway. And we're going to talk more about infinite limits, like I said, next week. But this is not a jump discontinuity because the one-sided limits don't exist. Okay. So we have that. It's not a hole. It's not a removable discontinuity. It's a jump discontinuity. There's a difference there, which hopefully we can see. If it was a hole, the limits would be the same. Like just maybe we would have a situation where the function wasn't defined. Or like, for instance, sometimes students are like, well, what if you had f of x equals 1 for x being greater than or equal to 1? And yeah, that would move this line down by 1 unit. And then you'd have a filled in circle and would go off that way. And yeah, then you wouldn't have a discontinuity at all. But because it's f of x equals 2, that's why you have the discontinuity. Yeah. Okay. So that's what I wanted to say about that one. We should state where it is continuous. So we could say that f is continuous on its domain, excluding the value 1. Okay, so 1 is the problem there. Okay. So let's talk about one-sided continuity at a number. All right, definition. One more thing to learn. All right, so your definition, one-sided continuity at a number. Let f be a function defined on the interval from A to C. Now we're keeping this open at A and we're closing it at C. Then f is continuous from the left at C if the limit as x approaches C from the left of f of x equals f of C. We can make a similar definition for being right continuous. So we could say if f is defined, and we'll switch the interval here. If f is defined on the interval from C to B, then f is continuous from the right at C. If the limit as x approaches C from the right of f of x is equal to f of C. So what you're looking for here is that the value of the limit is equal to the value of the function, or the value of the one-sided limit, I should say. Now going back to example D, because honestly, most of the time when we talk about one-sided continuity in a number, we're going to be thinking about this in terms of piecewise functions, most of the time. So back to example D, is f of x left or right continuous? So what you're looking for here is, for left continuity, you'd be wondering, well, as I approach 1 from the left, does my function value equal the value of the limit? So you'll check it. So in order to check for left continuity, you would be asking, does the limit as x approaches 1 from the left of f of x equal the function value? Well, as I approach 1 from the left, the limit is equal to 1. And then your function value at C is the function value at 1. Well, that's defined right here. So if x equals 1, f of x is 2. That's your function value. Because the limit value does not equal the function value, then we would say that f of x is not left continuous at x equals 1. But we can do something similar to talk about whether or not the function is right continuous. So you're going to take the limit as x approaches 1 from the right. And again, I'll go back to that graph. As x approaches 1 from the right, the limit is 2. You're always just sitting here on this horizontal line. But that's your limit, and the function value is going to be the same as it was before. It's always going to be the same for that whole function as long as I'm looking at x equals 1. 2 does equal 2, so f of x is right continuous at x equals 1. Because the limit as x approaches 1 from the right is equal to the function value. Okay. Let's talk about a couple different types of functions that we know something about, and we'll talk about their continuity. And then I'll give you some examples where you're going to have to tell me places just by looking at the function of where the function's graph would not be continuous. So let's discuss that. Okay. Theorems. Yay! A polynomial function is continuous on its domain. And its domain is, of course, all real numbers because it's a polynomial. Polynomials are smooth graphs. We don't have to worry about any sort of discontinuities in them anywhere. There's nowhere where you're going to divide by 0 because you don't have any variables in the denominator. So that's not going to be a problem. A rational function, remember a rational function is the quotient of two polynomials. A rational function, r of x equals p over q, is continuous on its domain, whatever that domain may be. Remember, the domain of that function is going to exclude any values for which the denominator will be equal to 0. So, gotta think about that. Let's see. We have some rules about sum and difference, product, and constant multiple. So if we're combining some functions, if f and g are continuous at c, and if k is a real number, then f plus g f minus g, f times g, and k times f are also continuous at c. Okay, so that means as long as f and g are continuous at c, then you can just take it for granted that there's some difference, product, and some constant multiple of that function would also be continuous at c. If g of c is not equal to 0, then f over g is continuous at c. So remember, we can't divide by 0. We can say something about the composition of two functions. You won't use this one quite as often. If a function g is continuous at c, and f is continuous at g of c, then f of g of x, the composite function, f of g of x is continuous at c. Let's see, if f is a one-to-one function, continuous on its domain, you remember one-to-one functions, I hope, from algebra, meaning one input gives you that one output each time. If f is a one-to-one function continuous on its domain, then its inverse, f inverse, is also continuous on its domain. Sorry, I'm trying to write a little bit neater. I'm trying to be conscious of that. I don't write with pen a lot. I feel like it's easier to be a little bit neater with pencil. Such is life. Okay, so we're going to use these facts to talk about continuity of functions that I am giving you in these examples. Determine where the function is continuous. So we're going to determine where the function is continuous. In this case, I'm not asking you to tell me, like, if there's a discontinuity, what type it is, or anything like that. I just want you to look at the function and think about what type of function it is and how the theorems that I just gave you are going to apply to its continuity. So A is going to be f of x equals 3x to the fourth plus 5x squared plus 3x minus 1 minus 2x over x minus 3. Now, I just gave you a theorem that said that a polynomial function is continuous on its domain, which is all real numbers. So this piece is a polynomial. Then I gave you a theorem that said that a rational function is also continuous on its domain. So a polynomial function, and then remember that rational function is the quotient of two polynomials. I don't need to worry about this one. The only value I need to worry about here is 3. If I let x be 3, the function won't be continuous. So I know that as long as x is not equal to 3, everything's fine. So if I'm talking about where the function is continuous, I can say that it's continuous on the interval from -infinity up to 3, and then all the way up from 3 to infinity. So you could say that c equals 3 is where your discontinuity is. I know we're going to talk more about asymptotes next week, but this would be a vertical asymptote. So you would expect that you would have this infinite discontinuity on your graph. Sorry, I have to stop yawning. I know it's not the most exciting stuff. Sorry. I know chapter 1, I feel like it's not as easy to teach just because it's a little bit like you kind of feel like you're trudging through it. Stuff gets a little bit more fun later on. It's kind of fun, but it's not like you're curve sketching or something, because that would be super fun. All right, so we found the interval in which this function was continuous for A. For B, f of x equals 2x times the square root of x plus 1. Okay, the polynomial is right here. Oh, and by the way, I didn't mention for A, this was just the sum or difference of two different types of functions, whereas like for B, we just have the product of two different types of functions. So we have a polynomial and a radical. Well, for the radical function, we need to exclude any value that's going to cause the radicand to be less than 0. So we need to force that radicand to be greater than or equal to 0. And that means that x has to be greater than or equal to -1. So my polynomial is going to be continuous everywhere. I know that the product of two functions is going to be continuous on their respective domains. So I can go ahead and say that our function is continuous for any value of x that's greater than or equal to -1. So that's the interval on which the function would be continuous. I can't say anything about any value of x that's less than -1 because this function wouldn't be defined for any of those values. And the whole function is limited by what the radical function can do in this case. Just like for how A, the entire function is very limited by the rational function. Now for C, we have f of x equals 5, or I'm sorry, x minus 5 divided by the square root of x minus 4. Okay. Now you have two issues here. First of all, you need to verify that your denominator is not going to end up being 0. So you need to make sure that this denominator does not equal 0. To do that, you can say that the square root of x cannot be equal to 4. And then square both sides, and you get that x cannot be equal to 16. So that's important, because if x is 16, well, then in the denominator, you have 4 minus 4, which is 0. Can't have that. But you also need to verify that x, or you have to force x to be some value that's going to be greater than or equal to 0, just because you need your radicand to be a non-negative number. So for this case, you must have that x is greater than or equal to 0. Must have. So we're not going to include any values for continuity that aren't in this function's domain. That means we're not going to include any values of x that are less than 0, because clearly we can't use them. They don't exist for this function. So let's go ahead. We'll start at 0, and we'll say that our function is continuous on the interval from 0 up to 16. And then remember, once we get to 16, we need to exclude that value, because it's going to cause the denominator to be 0. So we had 2 issues here. One of them was that you didn't want the denominator to be 0. The other was that you didn't want the radical to be taken with a negative radicand. So that is C. Okay. So that was 1.3. I'm going to put up some homework for that one. You guys can get a little practice looking at continuity. I just want to introduce 1.4 to you with some trig limits, just a specific type. And then I want to talk more about special trig limits on Monday. I'm just going to get your feet wet with these trig limits a little bit. And some of these you're going to see again in Calc 2. Uh, 1.4, limits and continuity of trig, exponential, and log functions. Limits and continuity of trig, exponential, and log functions. Now, the trig functions are what's going to take up most of our time in this section. The exponential and log limits aren't going to be too bad at all. And some of the trig ones can be tricky, others not so much. You just kind of have to practice them. But I do want to go over right now the squeeze theorem for some of these trig limits. And I think you'll recognize pretty quickly which limits the squeeze theorem would actually work really well for. Suppose f, g, and h have the property f, g, and h have the property that for all x in an open interval containing c, except possibly at c, we have to have f of x be less than or equal to g of x, which is less than or equal to h of x. If the limit as x approaches c of f of x equals the limit as x approaches c of h of x, and that limit is equal to L. Well, look what I've done here. I took the limit of the lower limit function and then the limit of the upper limit function, and both of those limits were the same, they were equal to L. As long as we can show that the limit of these boundaries is the same, then the squeeze theorem says that we can conclude that the limit of this middle function must also be equal to that limit L. So we can say then the limit as x approaches c of g of x must also equal L. And that's why it's called the squeeze theorem. You're taking this function g, you're squeezing it in between two functions, proving that if their limit is one specific number, then it must be the case that the squeezed function must also have that limit. And if you're wondering, like, okay, how would this be useful? Why would this matter? When would we need this? Well, sometimes you're going to have a hard time finding the limit of g, but you might be able to build functions f and h. And then as long as you can do that and show that g is between them and that f and h have the same limit, then you can make a conclusion about g without actually having to look at the limit of g. And of course, I'm going to give you two examples of that. Sometimes the squeeze theorem is also called the sandwich theorem. Sandwich, bread, bread, filler. Whatever that filler may be. Or if you're like my kids, only bread, no middle part of the sandwich. So there would be no g of x. Oh. They eat like prisoners. Example 1, use the squeeze theorem to find the limit. And I'm just doing example 1, A and B, and then the other ones we're going to work on Monday. Okay, example 1. Use the squeeze theorem to find the limit. Now these are going to be similar, but the first one is the limit as x approaches 0 of x squared times the sine of 1 over x. Now, you might be thinking like, well, why would I need the squeeze theorem for this? Can't I just evaluate this directly? No, because you can't actually take the sine of 1 over 0. So it doesn't matter that you're taking 0 times this quantity because you don't know what this quantity is. It's not just like taking 0 times a number. This might not be just some number. It could be infinite. We don't know. So the point is you're going to have to use the squeeze theorem since you have this situation where you're taking the sine of 1 over 0. That's problematic. What you're going to do for these types of questions, and it's pretty much always going to apply to trig, and for our intents and purposes, you're going to take the trig function first, and you're sort of going to build this out using the squeeze theorem. So I'm going to start with the middle right here. And I'm going to take my trig function, and I'm going to set up an inequality, and I'm going to say something that I already know about this function. For instance, a lot of you just took trig. We should know the range of the sine function. You're not going to get a value for sine of any quantity that's greater than 1 or less than -1. The range of the sine function goes from -1 to +1. And it doesn't matter what's inside your sine function. Doesn't matter. Sine of any number can never be more than 1 or less than -1. So we can use that fact to squeeze our sine function in between these two boundaries. You can kind of see what I'm doing now. So this function inside my inequality is going to be my g of x, but I have to build it so that it matches the given function in example 1a. I'm close. Right now I have just the sine of 1 over x. If I need this function to match, then I need for it to be x squared times the sine of 1 over x. But that's fine, because I can force it to be x squared sine 1 over x. But what I do to one part of the inequality, I have to do to all three parts. So if I'm going to multiply by x squared there, then I also need to multiply by x squared on the outer edges or the outer pieces of this inequality. So this is how we're using the squeeze theorem right now. So we took a function that was very complicated, but we used the fact that we knew something about the range of the sine function, and we were able to get these more simple quantities to work with. And then even though we still had to build this up and multiply through by a function of x, it was an easy function of x. So what I'm going to do now is I'm going to show that our outer functions, f and h, must have the same limit. And if that's the case, then g has that limit too. So we can say that the limit as x approaches 0 of, well, let's look at the left first, negative x squared equals 0. It must, because remember, it's a polynomial function, and we can find this limit using direct substitution. I can do the same thing with the right-hand boundary. The limit of x squared as x approaches 0 is 0. And that's all we have to do. So we can say, okay, we found these two, hence the limit as x approaches 0 of x squared times the sine of 1 over x equals 0 by the squeeze theorem. So there it is. I'm going to do one more of these that's slightly more complicated, but these are all basically going to work the same way. And I've actually found that students do pretty well with the squeeze theorem. They don't like it at first because it just seems scary and weird and different, but you get used to it and start to think this is not too bad. So the next one would be the limit as x approaches 0 from the right of the square root of x times e to the cosine of pi over x. And again, don't be intimidated by the fact that we're approaching 0 from the right. We have to, I'm sorry, if we approach, yes, 0 from the right. We have to approach 0 from the right. I mean, look at this function. Its domain is only values of x that are greater than or equal to 0. I can't take a value of x that's less than 0. I cannot possibly approach this value as I cannot possibly approach 0 from the left on this function. Just won't work because it's not defined for values that are less than 0. Okay, so the square root of x times e to the cosine of pi over x. And again, if you're like, oh, no big deal, I'll do this using direct substitution, well, that's going to be a problem for you for the same reason that it was a problem for A. You can't take the cosine of pi over 0. You don't know what that is. You can't divide by 0. So you can't say, oh, 0 times the cosine of an undefined value is 0. It doesn't work that way. You're going to have to use the squeeze theorem. Start out with your trig function. We're going to build this up. I know it's in the exponent, doesn't matter. Start off with your trig function always, just your basic trig function. We already know that sine and cosine are bound between -1 and +1. And then we're just going to work our way from the inside out. Don't work with your square root of x yet, because that's the last thing we're going to do. First, I need to build up this exponent. I can turn this into e to the cosine of pi over x, but what I need to do then is raise both sides such that they have a base of e. So if I'm going to make e the base in the middle, I need to also make e the base on both of these ends. And then the last thing I have to do, so that was the trickier part. The last thing I have to do is multiply through by the square root of x, and then I'll get it to match. E to the -1 is the same thing as 1 over e. So if you want to write it like that, I think it looks better, but that's up to you. I cannot force you to do that. Okay, now it matches. So now my goal is to show that the limits of these boundaries is the same. And then I can make the conclusion that the limit of this inside function must be the same as the limits of the boundary functions. So I'll do that next. So we'll take the limit as x approaches 0 from the right. I'll start with the left-hand boundary. The square root of x over e. Well, for this limit, if I let x approach 0 from the right, 0 divided by a constant, remember e is a constant, is 0. Work on the right-hand boundary. The limit as x approaches 0 from the right of the square root of x times e. Then you have 0 times a constant, which is 0. So we can say, by the squeeze theorem, the limit as x approaches 0 from the right of the square root of x, e, to the cosine pi over x, must also equal 0. So let's say I put this on a test and I gave you this question. I would be expecting you to use the squeeze theorem. So if you just said equals 0, you're not going to get credit for that because I'm expecting to see your work. The directions will say, make sure you show your work to justify your answers, blah, blah, blah. And if you said like, oh, well, isn't it obvious that the limit is 0? No, it's not obvious. It's not obvious. You need to justify this by using the squeeze theorem. So, I mean, it's a situation where if I gave you this in a table section, you probably could have used the table to find this. I'm going to guess this one oscillates quite a bit, and it might not be the easiest thing to find in a table. I might be wrong, but this would definitely be put in a section. If I wanted you to use the squeeze theorem, I would say find the limit analytically. The squeeze theorem is an analytical way of finding a limit. It's not a table. It's not graphical. So this would definitely be in an analytical part of your exam. All right, so that's how to use the squeeze theorem. I'm going to put up some homework questions on that so that you can kind of get your feet wet. And then we'll talk about basic trig limits and how to use them on Monday. And then we'll also talk about those log and exponential limits, which are no big deal. Yeah, but that's all. Hopefully that wasn't too crazy. We're on target, so that's great. And I hope you guys enjoy the rest of your weekend. I'm going to put up some homework, so don't forget you have homework from 1.2. And then you'll have the homework from this, which is 1.3 and just a little bit of 1.4. I think it's probably like 2 or 3 questions for the squeeze theorem. I can't remember exactly, but I'm gonna put that up right now for you so you can get started right away. Okay, that is all. You have a quiz on Monday, and it will cover 1.2, 1.3, and technically it could cover the squeeze theorem, although I don't really know that I would put that on a quiz. But yes, quiz Monday. Your homework will be due Monday from 1.2, 1.3, and whatever I assign for squeeze theorem. If you have questions, please email me. If it's something on WebAssign, go ahead and send me a message through there so I can see what problem you're working on. Okay, that's it. Have a wonderful weekend, everybody. Bye.